Welcome to the introduction of Paul Flory, famously dubbed the architect of macromolecules. This slide sets the stage for a journey into how Flory brought essential mathematical rigor and physical order to the giant, often chaotic molecules of the 20th century. Visually anchored by a stark red cube on a precise geometric grid, the imagery beautifully reflects his life's work, taking complex, tangled polymer chains and defining them through structured, predictable frameworks. He didn't just study polymers, he gave them a structural blueprint, forever changing the landscape of modern materials science. Paul Flory's legacy is defined by a powerful duality: the scientist and the activist. On one side, he brought order to empirical chaos, transforming the trial-and-error industrial chemistry of plastics, rubbers, and fibers into a rigorous, mathematically sound discipline rooted in thermodynamics. On the other side, he was a fierce defender of the global scientific network. Flory used his immense global prominence to fight tirelessly for human rights, standing up for oppressed and dissident scientists restricted behind the Iron Curtain. Together, these two pillars showcase a man dedicated to truth, both in the laws of physics and in the defense of human freedom. This slide traces the foundational chapters of Paul Flory's early career. Node 1. The foundation spans from his roots in Sterling, Illinois, through Manchester College, where he overcame early insecurities in mathematics to earn a PhD in physical chemistry at Ohio State. Moving to Node 2. The catalyst, Flory joined E.I. DuPont de Nemours to study the physical mechanics of linear chains. This crucial period sparked the Carruthers influence. While Wallace Carruthers famously proved that macromolecules were linear chains of covalent bonds, it was Flory who provided the essential statistical mechanics to truly understand and manipulate them, bridging the gap between structural theory and mathematical reality. This timeline illustrates Paul Flory's unique career trajectory, which constantly oscillated between practical industry labs and universal academic theory. On the industrial side, Flory tackled immediate commercial challenges, studying condensation polymers at DuPont in 1934, developing synthetic rubber for World War II at Esso in 1940, and investigating vulcanized networks at Goodyear in 1943. Each practical stint fueled his academic breakthroughs, leading to a mathematical theory of gelation at Cincinnati, solution thermodynamics at Cornell, and matrix methods at Stanford. The core takeaway is clear. Flory used his transitions between corporate labs and universities as the engine of his genius, seamlessly transforming immediate industrial problems into universal physical laws. This comparative matrix contrasts classical assumptions with the Flory reality, highlighting how Paul Flory redefined macromolecular physics across four critical dimensions. For reactivity, old models assumed a sluggishness as molecules grew. Flory proved the principle of equal reactivity, showing localized reactions independent of length. For solution entropy, he replaced inadequate ideal gas analogies with lattice volume fractions, which account for massive size asymmetries. Regarding chain shape, he updated the ideal random walk assumption to incorporate excluded volume, recognizing that real chains repel themselves and expand. Finally, for network behavior, Flory replaced simple stoichiometry with his gelation theory, identifying a diverging weight-average molecular weight. Flory fundamentally rewrote the rules of polymer science. This slide details the three-step chain transfer relay, a fundamental mechanism for regulating polymer size. In step 1, a growing polymer chain hits a physical or kinetic wall. In step 2, the active radical end steals a hydrogen atom from a nearby monomer or solvent molecule. Finally, in step 3, the original chain becomes dead, but the radical baton is passed to initiate a brand new chain. This elegant relay mechanism provided the mathematical explanation for how to regulate average chain lengths and manage polymer size distributions, a breakthrough discovery that proved absolutely critical to the success of the U.S. synthetic rubber program during World War II. This slide illustrates two breakthroughs in polymer physics. On the left, the gelation explosion shows that gelation is mathematically analogous to a branching nuclear chain reaction, where a sudden network expansion occurs. On the right, the Flory-Renner swelling balance defines the equilibrium state of a cross-linked polymer network in a solvent. It visualizes the opposing forces at play: the thermodynamic mixing force pulling solvent in, and the elastic retractive force pushing out. Represented by the equation below, this equilibrium is reached when the desire for the solvent to mix exactly balances the network's elastic retraction, providing a precise mathematical description of polymer swelling behavior. This slide introduces the Flory-Huggins model, contrasting a classical solution with a true polymer solution. In a classical solution left, molecules are of similar size, allowing entropy to be modeled simply via mole fractions. However, a polymer solution right features massive size asymmetry, requiring entropy to be modeled via volume fractions on a lattice grid. The core thermodynamics are defined by the equation shown. Central to this model is the Flory interaction parameter, chi, which accounts for the critical energy difference between polymer and solvent contacts, providing the foundation for understanding polymer miscibility. This slide explores the physical chain and excluded volume, highlighting how Paul Flory corrected a major classical assumption. While earlier theories assumed polymer chains could cross themselves like ideal random walks, Flory proved that real chains occupy physical space, possessing excluded volume, that causes them to repel themselves and expand. He mathematically captured this behavior through the formula on this slide. The key insight here is the Flory exponent, nu equals 3/5 equals 0.6. By balancing the entropic penalty of chain expansion against the energetic cost of monomer contacts, Flory derived a simple, brilliant approximation that perfectly matches highly complex, modern renormalization group theories. This slide details the Flory theorem, melt screening and the theta condition, utilizing a balance scale to visualize a fundamental equilibrium in polymer physics. On one side sits excluded volume, driving chain repulsion and expansion. On the other is intramolecular attraction, causing chain collapse. The center indicator marks the theta condition, the precise point where these opposing forces perfectly balance. A key application is melt screening. In a dense polymer melt, the excluded volume interactions of a given chain are completely screened by surrounding chains. With no net drive to expand or collapse, the polymers behave ideally, adopting unperturbed, ideal random coil conformations. A profound insight that simplified the mathematical analysis of complex polymer liquids. This matrix presents Paul Flory's elegant mathematical solutions to 4 foundational problems in polymer behavior. First, for step growth molecular weight, the Flory-Schultz distribution provides a precise probability model. Second, the polymer glass transition temperature is defined relative to molecular weight using the Flory-Fox equation. Third, for polymer blends, the Fox mixture equation calculates the resulting transition properties of mixed materials. Finally, backbone stiffness is quantified using the characteristic ratio, C infinity. Accompanying these formalisms, a bond rotational energy diagram for N-butane underscores how these macroscopic properties are fundamentally dictated by microscopic, angle-dependent torsional energy barriers, completing Flory's vision of a mathematically rigorous macromolecular physics. This slide celebrates the pinnacle of Paul Flory's recognition, charting his monumental accolades in 1974. On the left, we highlight his 1974 Nobel Prize in Chemistry, awarded for his fundamental theoretical and experimental achievements in macromolecular physical chemistry. On the right, we note the 1974 National Medal of Science, presented by President Gerald Ford for his definitive contributions to the physics of plastics, rubbers, and fibers. The core takeaway beautifully bridges these honors. Flory was celebrated not for a solitary discovery, but for single-handedly transforming polymer science from empirical guesswork into a mature, highly structured branch of physical chemistry, forever organizing molecular chaos into mathematical order. This activist organization was built specifically to defend oppressed Soviet dissidents, including an exiled nuclear physicist, an imprisoned accelerator physicist, and an imprisoned mathematician, proving that Flory's commitment to freedom spanned far beyond the boundaries of American academia. This slide illustrates the aggressive, high-stakes methods Paul Flory deployed to shatter Soviet stonewalling and censorship. Striking energy beams break through a dense stone barrier, Visualizing 3 disruptive tactics. Tactic 1. The scientific moratorium mobilized over 8,000 international scientists in a voluntary boycott, starving the Soviet state of Western technological prestige. Tactic 2. Direct broadcast bypass state censorship by transmitting directly to dissidents behind the Iron Curtain via the Voice of America. Finally, Tactic 3. The hostage offer details Flory's ultimate moral sacrifice in 1984, offering himself as a political hostage to guarantee the release of Elena Bonner for life-saving surgery. These actions cemented Flory's legacy as a scientist willing to risk everything for human freedom. This concluding slide serves as a profound epilogue to the life of Paul Flory, offering a final reflection on his comprehensive legacy. It synthesizes his dual identity, emphasizing that his contributions cannot be measured solely by mathematical equations or chemical breakthroughs. Flory proved that a world-class scientist can, and must, simultaneously act as a global moral leader. By championing both physical truth in the laboratory and human freedom on the international stage, he left behind an enduring blueprint for future generations. His life stands as a powerful testament that intellectual genius and human empathy are not separate paths, but deeply intertwined forces capable of reshaping the world.